We ended the first section at page 15. I move forward now to page 22. I'll go back to page 15. Going from page 22 is instructive and helpful. So let me just tell you what we are trying to do. Before we went on break, we tried to explain what we mean by a transformation. Transformation, we said it was a rule, a process. Once you can explain it in any way, and we know what you are talking about, that's a transformation. A transformation has an input, what you are transforming. It has an output, the result of the transformation. For instance, in case of the sun, the rule is that you represent a vector by a stick with a direction. You place that vector in the sun and you have a plane. You have a plane surface that a shadow can be cast upon. We say that if that happens, the shadows are also vectors because they have magnitude and direction, and that transformation is linear, because if you have two vectors, you are going to get two vectors that are equal. You are going to get a transformation that are also two vectors that are equal. If you put them on top of each other, you are going to get a shadow that is twice the length of the shadow of either of them. If you have three vectors, they are going to be transformed in proportion to their sizes. And that once you have such transformations, you say that the transformation is linear. We are going to be more specific about linearity by example. Many times when you do not understand an idea very well, by the time you now see a few examples of that idea, when that idea is taken true and you see that the idea conforms to the definition over and over, it reinforces the theory and it helps you to understand. So what I want to do now is to supply 7 different transformations. 7 different transformations. And once we agree that these transformations transform vector to vector and that their transformations are linear, that means that I've introduced 7 tensors to you. I'm going to introduce 7 different transformations. We are going to check if you supply a vector to this one, do you get a vector back? If you supply 2 vectors, you get 2 vectors back. Does it transform linearly? Does it transform proportionally? If it does, then we say it's a tensor. Then that means that I've introduced 7 tensors to you. So let me start by enumerating them. There are 2 things to do, because I want us to be very clear when we are introducing the transformations, and I want us to separate that to the proofs that there are transformations that are linear. I will not do the proofs of the linearity today. I'll wait for next week. We can wait, because I want it to sink into you what these transformations are. Just understand the transformations today. The next week, we will be able to now show that the transformations are linear and therefore they are all tensors. We will show that they are tensors next week. But today, we are just going to be sure that you understand the definition of the transformation, because it is even more important that you know the definition of the transformation that you can prove any mathematics with it. Many times, our problem is that we do not understand what we are dealing with. We are rushing to do mathematics. Don't do any mathematics. Understand what the definitions are first. Once the definitions are clear, you will see that the mathematics is almost trivial. There's not much in the mathematics. Your problem often, or our problem often, not only you, even me too, is that we do not understand the definitions well enough before we start cramming and pouring and calculating and measuring. Okay, the 7 transformations I'm going to introduce are, the first one is the projection or shadow, like the shadow of the sun. You will see that we can dress up the shadow or the projection in mathematical dress. We can clothe it mathematically, and I can give you a mathematical formula that corresponds exactly to a shadow. So, because it will when you apply it to any vector, it will do what the sun does to sticks exactly. If you calculate what it does, the way it does it, this mathematical, what do you call it now? Is it mathematical juju that I'm going to give you? Does the same thing as the sun. and it is called the projection transformation or the projection tensor. Then the second one will be the coordinate transformation. I will explain to you what a coordinate transformation is. Once you understand it, you will see later on, we will prove that it transforms vector to vectors and the transformations are linear. I think I introduced the dyad in the last course. I will introduce the dyad again, and this time we will prove that it transforms vector to vector as this is defined, and that the transformations are linear. Then we will introduce the identity tensor or the identity transformation. We will show again that that identity transformation, you supply a vector, it gives you a vector, and the transformation is linear. Then we will introduce the annihilator transformation. And we'll show you that the annihilator transformation transforms tensor to tensor and does it linearly. We introduce the spherical transformation. We again show that the spherical transformation transforms vectors to vectors and it does it linearly. And therefore, it's a linear transformation and it is a tensor. Then we are going to introduce the most familiar of them. You may not know it is familiar, but by the time we finish, you will see that it is another concept you have known in a different way, but you are going to know it in new. It's going to wear, when you knew it before, it was wearing a t-shirt. Today, it's going to wear a tuxedo, but it is the same person. You see, you saw somebody before, maybe you saw somebody last year, he was wearing a t-shirt. This time you saw him wearing an army uniform and you forget that it's the same person you are looking at. All that has changed is the cloth that is on the body. The vector cross is something you are familiar with. You are familiar with the vector cross from a vector point of view. We're going to introduce the vector cross as a tensor. You will see that the vector cross is actually not a vector, but you have been dealing with it as a vector all the time. You will see that it is actually a tensor, and it is actually much easier dealt with as a tensor than it's a vector. I will show that the vector cross is actually a transformation. If you supply a vector, it gives you a vector, and that transformation is linear. So, as I said, I am going to just introduce them today, and I will just let you go and rest with the definitions so that you think about them. So next week, I will take them one by one, and I will prove that each one transforms vector to vector linearly. And therefore, the projection is a projection tensor, the coordinate transformation is a coordinate transformation tensor, the dyad is a dyad tensor, the identity is an identity tensor, the annihilator is the annihilator tensor, and the spherical transformation is the spherical tensor, and the vector cross is the vector cross tensor. And they are all the 7 of them are tensor. I just chose those 7 examples, and I will be taking you all again. I will be taking you to the definitions on page 14. I'll be taking you back to the definitions on page 14, and there, I think, was it on page 14? No, it's not on page 14. The definition on page 12. We'll be revisiting it over and over, and we shall find that these things are actually they're actually tensors. So these are, like I said, they are simple tensors. So let us start with the coordinate transformation. I want to show you that a coordinate transformation is a tensor. But let me define today, I will define the coordinate transformation. Are you seeing my page 15, class? Can you see my page 15 yet? Let's see. Let me just see whether you are seeing my page 15. Please tell me in the chat room if you can see my page 15. Okay. You can see my page 15. Good. Can you see the blue coordinates? You can see the blue coordinates that have E1, E2, E3 as unit vectors. Can you see the blue coordinates that have E1, E2, and E3 as unit vectors? Okay, so you've seen that. Now, the pink coordinates, I hope it is pink. The one with the other color, I don't know color, I'm sorry. They have Xi1, Xi2, and Xi3 as their unit vectors. you can see that you can go from the first set of coordinates to the other by rotation. We did a rotation. And what it therefore means is that if you had a vector in the original coordinate system with components that you know, you can find the components in the new coordinate system. That component in the new coordinate system will define another vector. You see, the thing was a vector in one coordinate system. It will be another vector in the other coordinate system. And we can find its components. So, what is the input vector? The input vector is the vector in the original coordinate system. What is the output vector? The output vector is the same vector in the new coordinate system. What we are saying is that there will be a relationship between the new coordinates and the old coordinates. And that we can show from that relationship that transformation is linear. If we show that, then that means that coordinate transformation is actually a tensor because it changes a vector from one vector, it changes a vector to another vector, because the vector you will see in the first coordinate system is different from what you will see in the second coordinate system. If that is difficult for you to understand, let me make it very simple. Suppose the vector we are dealing with, is the vector xi1. If it is vector xi1, it will have a component along E1, it has a component along E2, and it also has a component along E3. So, but when we get to the second coordinate system, it has no component, it has only component along xi1, but it doesn't have components along. So it will be something on xi1 and 0, 0 on xi2 and xi3. So whereas it can have alpha E1 plus alpha E2 plus beta E2 plus gamma E3. But when it gets to the second coordinate system, it will just be something xi1 and 0, xi2, 0, xi3. So you can see that we are dealing with, from the point of view of each coordinate system, we are dealing with two different vectors, because one is just 0, 0 on the two other components, but this first one, so the figure depicts the coordinate transformation. If a vector V was fixed to the original autonomous coordinates in such a way that it moved with it, what would be the coordinates in the new system? What would be the coordinate in the old system? What would be the resultant of several vectors? How will the resultant of several vectors transform? What about a weighted average, a weighted sum of vectors? What is the relationship between the image of a weighted sum of vectors and the image of the weighted and the vector sum of the image? The image of a weighted sum and the vector sum of the image. So those are the kinds of things. So a coordinate transformation will eventually be shown to be a tensor. The dyad. We encountered the dyad product of two vectors in the last chapter. Recall that a dyad is defined by the way it transforms vectors. We know that the result of the transformation is another vector, satisfy the first requirement. But is the dyad a tensor? We will reach that conclusion by the answers provided to the questions we have been raising. If the dyad operates on the sum of two vectors, the weighted sum of several vectors, and the scalar multiple of two vectors, etc., what is the relationship between the transformed vectors and the originals? Will the image of the weighted sum of two vectors be the sum of the images of those vectors if they were transformed individually? So let us say I have two vectors, A and B, and I got two other vectors by transforming them on their own. Or suppose I now add them together. Will the result I have got be the same as the sum of the original result? If it is, then it's a linear transformation. If I have the weighted sum of several vectors and I transform the result, will it be the same as the weighted sum of the images? If I did the images in the transform section, will I get the same thing? If I have a scalar multiple of two vectors, if I have a scalar multiple, am I going to get the vector, the image of the scalar multiple in the transformed system? Let us look at another one, the identity transformation. The identity transformation will look trivial to most of you. It will look trivial. We represent the identity transformation by the symbol I. Its characteristic may at first look appear trivial. It does absolutely nothing to the vector it transforms. That is, it doesn't change anything. Mathematically, for any U that is a member of the Euclidean vector space, if you operate I on U, you just get U. It changes nothing. A transformation that doesn't do anything, you get V. What about IU plus IV? Because this is U plus V. Again, if you get the same thing, then that means that it's linear. What if you transform a weighted sum, alpha U plus beta V? Are you going to get the weighted sum of the transforms? Or if you transform a weighted sum, are you going to get the weighted sum of the transforms? Questions. Is the identity transformation of a sum equal to the sum of the identity transformations? Is the identity transformation of a scalar multiple equal to the scalar multiple of the identity transformation? Is the identity transformation of a weighted sum equal to the weighted sum of the identity transformation? You can replace the identity transformation by any of the 7 that we have introduced. If the answer to all of them is yes, then what you have is a tensor. If the answer to any of them is no, that means that what you have is not a tensor. Let us look again as another example, the annihilator tensor. What does the annihilator tensor do? The annihilator tensor produces the 0 vector for any vector it operates on. So if you operate it on U, you get 0. You operate it on V, you get 0. You operate it on W, you get 0. You operate on anything, you get 0. But is that transformation linear, that annihilation transformation? Is it linear? So if you operate it on U plus V, do you get what you get from the sum of what you operate U? Because when you operate on U alone, you get 0. When you operate on V alone, you get 0. 0 plus 0 is 0. Suppose you operate it on U plus V. Does it also give you the same result, which is still the same 0? If you operate it on the weighted sum, does it still give you 0? If it does, or if it answers all these questions, then it is a tensor. What about the spherical transformation? The spherical transformation is the identity transformation multiplied by a scalar. So S is like, there must be a gamma U, which is a real number. When you multiply it by the identity tensor, you get the tensor called the spherical tensor. It is simply a scalar multiplied by the identity tensor. Again, if you put the identity tensor, is the identity tensor of the identity tensor transformation of a sum equal to the sum of the identity, is the spherical transformation of a sum equal to the sum of the spherical transformations? Is the spherical transformation of a scalar multiple equal to the scalar multiple of the spherical transformations? Is the spherical transformation of a weighted sum equal to the spherical weighted sum of the spherical transformations? If the answer to every question there is yes, then you have that the spherical transformation is the spherical tensor. If the answer to all the questions asked above is in each case that the transformation of a sum is the sum of individual transformations, this transformation of a scalar multiple is the scalar multiple of transformation of the initial vector, the scalar multiplication, the transformation of a weighted sum is the weighted sum of the transformations of the constituent vectors in the same weights. Then we can conclude we are dealing with tensors, that is second order tensors. The transformations we have discussed are all therefore linear transformations, and because they transform vector to vector, they are also therefore tensors. So these are the 7 examples, and the identity. So from this point on, from page 24 on, all I am doing is proof. I will prove until the end of the notes here. But I don't want to bother you with that today. I want you to drink and digest the questions that we are posing. Understand those questions, because we will answer those questions next week. I want to leave it there. I don't want to go beyond that today. So if you can, what I want you to do You can read the entire thing from page 1. That is, read the book from the first page till where we are now. And let me know in the next lecture, the issues that you are having with it. And then also, as soon as the admin makes the site available, begin to do your self-testing. Self-testing will help you to answer better questions. And I advise you, do as many as 10 self-tests before the exam. And you'll see that it's not hard to do well, to do very well in this course. And when you do very well in the course, you yourself know that you know the course. Nobody needs to tell you that. You know the course. So that there's a confidence you gain when you do your self-test and you do well in it.